All right, so our next little example is, looks like a little product rule. So it's got 2x. Remember, the 2 goes either with the x or the cosine. I'm going to just place it with the x. I have 2x times cosine y, so there's a little product rule. And since this is the product rule, I'm going to go ahead and say first times derivative of the second plus second times the derivative of the first. I'm going to write out the product rule so I don't make sure we don't forget any pieces. And that's equal to, we'll do that later. First, copy paste, derivative of the second, negative sine y dy dx. First times derivative of the second plus second, copy paste, times the derivative of the first, well that's just 2. And then the derivative of the right-hand side, derivative of a constant is 0. Now let's see. All the dy dx terms go to the left. All the non-dy dx terms go to the right. And I'm going to clean things up as I go. This implies this. This implies, kind of clean this up as we go here. What do we have here? We have negative 2x sine of y dy dx. And then this needs to move to the other side of the equation. And I'm going to throw this 2 out front as a coefficient. So this is negative because I have to move it across the equal sign. There we go. And what's left is to solve for dy dx, which means you've got to divide both sides of the equation by this little expression here. And so this is negative 2 cosine y over negative 2x sine y. If you like, you can just put a box around it and be proud of it. That's fine by me. If I had to bet money, the textbook's not going to have this. The textbook's going to cancel those negative 2's. So if you like, and if you're proud of yourself, you can cancel the negative 2's. That's more than fine. That's just spectacular and glorious. Some people are just even more, they're more proud of themselves. Cosine over sine is cotangent. So if you really, oh my goodness, if you're really feeling your wild oats, you can write this as cotangent y over x. I have no idea what version the textbook would have. My guess is probably that. But as far as I'm concerned, as soon as you find dy dx, just there it is, back away slowly and don't make eye contact. So that's the procedure for implicit differentiation, finding the derivative. Now, the next piece is this. What if we have a problem just like before? Before, when we had curves, we could find equations of the tangent line. You would need to know the point that lies on the line, x0, y0, would be the point of tangency. And you would need to know the slope, but the slope was given by the derivative. Well, now the difference is we might have x squared plus y squared is equal to 25 at the point, and it might be, let's say, negative 3, 4. Now, we know what that graph is. We know because we've been through basic algebra. We know that that is the equation of a circle of radius 5. So if I have a circle of radius 5 at negative 3, 4, that's my point. And certainly there is a tangent line there. But to find the slope, I don't get to use f prime because that's not what this represents. The slope is dy dx. Now, we actually find f prime. The slope is actually found by you take f prime, evaluate it at x0. y0 doesn't go into finding the slope because this is an explicit function of x. But here, we are going to potentially have both x's and y's in this expression. Both negative 3 and the 4 will go into this computation. You'll see this happening as we go there. So here's the procedure for if you're given an expression that requires implicit differentiation and the task is to find the equation of the tangent at negative 3, comma 4. The tangent line at negative 3, comma 4. All right? So, well, what do we know? Well, let's just get rid of this part of the picture. We don't need that. We do know we have y minus y0 is equal to slope times x minus x0. That's always the case. And x0, y0 are the given coordinates, right? So we do know we already have y minus 4 is equal to, don't know yet, x minus negative 3. And we'll fiddle with that later. Our task is to find the slope. And the slope is given by the derivative evaluated at the given information. So we need to find dy dx. Well, dy dx, we find dy dx the way we've been doing it for a while now. This term does not involve y. The derivative is as usual. This term does involve y. So we multiply by dy dx. This term does not involve y. The derivative is as usual. The derivative of a constant is 0. Solve for dy dx. So 2y dy dx, this stays on the left-hand side. This has to move to the right-hand side. Divide out the 2 y's. So dy dx is given by negative 2x over 2y. You may or may not, as is your desire, you may or may not cancel the 2's. Let's suppose we do cancel the 2's. So what we end up with is negative x over y. Now how do we use that and this information to find the slope? You don't put negative x over y in this equation. We don't want that. What we need to do is to evaluate this at the given information. So I'm going to move my picture over here. Right over here. We need to evaluate dy dx, which is equal to negative x over y. Evaluate that at, what are my given values? Negative 3, comma 4. Here's the way we write that. The slope is negative x over y. And anyone who knows what you're doing knows what this symbol means. This is standard symbol. It's in the text. It's all over the place. You can simply write a vertical line. If you write a vertical line to the right-hand side of an expression, vertical line to the right-hand side of an expression, you read this as evaluated at. So this vertical line is evaluated at. And then down near the bottom of the expression, you write negative 3, comma 4. So the slope is negative x over y evaluated at negative 3, comma 4. This is the given point we were working with. Now, the textbook and most people tend to write vertical lines. I learned this a little differently. It is part of my DNA. There actually are some advantages to it. But I will do this slightly differently. What I will always do, rather than the vertical line, if you just use the vertical line in this case, that's fine. But what I will always do, I will always put my expression in brackets and write it this way. This also means evaluated at negative 3 to 4. There are some advantages to this, and if you do it this way, you will avoid some problems you never even knew were there. But I will always write this with brackets. So this is, the slope is negative x over y evaluated at negative 3, comma 4. And what that means is you substitute in negative 3 for x and 4 for y. So the slope is equal to negative 3 over 4. The negatives cancel. The slope is 3/4. And so that's what goes into here. And then we simplify that expression. I'm going to run out of space here, so I'm going to kill my picture. And so I have y minus 4 is equal to, this is 3/4 x. This is plus 3, so this is plus, top times top, bottom times bottom is 9/4. And then add the 4 across. 9/4 plus 4. What, 4 is 16/4? Is that right? 9/4 plus 16/4 is 25/4. So, luckily, you're good at working with fractions. If you were bad at working with fractions, you'd have a rough time. But luckily, you're good at that, so there's no problem with there. All right? So that's the key. So find the expression, evaluate dy dx. Evaluate it at the given point, substitute and simplify, and then compute the equation of the line.